Welcome back to my channel. Today we are going to continue our discussion on dynamic programming, and we're going to start with one of the first dynamic programming patterns, the Fibonacci numbers. Please, if you need to go back to the previous video to get an introduction to dynamic programming, please do, because I would most likely not discuss some of the things I did discuss on the introduction. So we mentioned that when it comes to dynamic programming, we have a situation where the question or a solution to the question needs to exhibit some properties. The first one is it needs to have an optimal substructure. We already explained what that means. Second is that it needs to have the subproblems need to be overlapping. So we see overlapping subproblems. So if we have a question that fulfills these two properties, that means the question is amenable to dynamic programming. So let's take the first one. So when it comes to Fibonacci numbers, we already gave an example of how this satisfies dynamic programming, but then let's just discuss it a little bit further. So the first property is when Fibonacci numbers, first of all, the series of numbers that starts from 0, 1, yeah, and then goes on to 1, and then every number is now the sum of the two previous numbers. So we'll have 2, we'll have 3, this will be 5, and then 8, then 13, 21, then this is 34, that way. So we said that fib of n is equal to fib of n minus 1 was fib of n minus 2. And then highlighting the fact that when we have fib of 1, just return 1, and when we have fib of 0, we have 0. Yeah, so this is an optimal substructure. We explained that, and then we also explained why the subproblems are overlapping. Yeah, but let's take that a little bit further. Okay, so the optimal substructure part is kind of clear. Yeah, so we can see this, and then we can see this. We need to break the problem down. In fact, this problem by default needs to be broken down into subproblems, and then we now need to perform some combination of those two subproblems to form the original to generate a solution to the original problem. Yeah, in this case, we need to sum them together. So this is the optimal substructure part. Now to the overlapping subproblems part. Now let's say that we hypothetically want to figure out the fib of 5, and we draw a tree. So there is the concept of a decision tree that kind of makes the concept clearer. So we will have a fib of, let's say we want to calculate fib of 5. So we have fib of 5. In calculating for fib of 5, we will do, so this is fib of 5. Remember, we need to break it down into fib of 4 and then fib of 3. And then we sum them together kind of. So the fib of 4, we need to have fib of 3 and fib of 2. Fib of 3 needs to be broken down into fib of 2 and fib of 1. Remember, 2 also needs to be broken down into fib of 1 and fib of 0. 1 is 1. This 2 also needs to be broken down into fib of 1 and fib of 0. So at the same time, we need to break this down into fib of 2, fib of 1. This needs to be broken down into fib of 1 and fib of 0. So if we take a look at this whole picture, remember we spoke about trees the other time, so this is what is the decision tree. So when we try to solve for the first part, for the first problem, when we try to solve for this one, we need to split it down into these two and then solve for each part. recursively. So we keep attempting to solve for each part recursively until we get a solution for p of 1. Then our function call now speeds up the solution to this, yeah, and then we make a second recursive call which also speeds up the solution to this. Then we sum both of them together to get the solution for fib of 2. Now having a solution to fib of 2, we speed up that solution back, and the recursive function call, from this point also attempts to solve this one, which returns it back. So you see all of these points here, this fib of 1, fib of 0, all of this, they are things that we call the base case. Yeah, so we can no longer break them down into further solutions. Like we can no longer say fib of 1 would be, if you imagine fib of 0 and fib of -1. Yeah, so that's like -1, 1 minus 1, and 1 minus 2. So this is, this is technically not possible. So these are the base cases, 0 and 1. Yeah, so this is the last we can go. So that's why they are considered to be base cases. So fib of 1 and fib of 0, they're base cases. Remember from this point, from definition, that was why this is important. So now that we have the base cases, we know that once we go all the way down to the base case, we can really now split up our answer, right, from the function call, and then from here we just get back this answer back. Yeah, so the issue here now is that if you take note of what's going on here, there's a lot of fib of 0 and 1 going on. Yeah, so this is a lot of fib of 1, but then speed of 1 and fib of 0, they are not breaking down. They are all base cases, so we just immediately return back from them. Yes. However, when it comes to fib of 2, this is a fib of 2. Yeah. Calculation is happening several times. This is 2. This is another one. Fib of 2. 3 different times. In this whole decision tree at 3 different points. We need to explore the calculation of fib of 2. Same thing when it comes to fib of 3. So let me just okay, let me use a different color. So fib of 3, we calculate it here the first time, and then we calculate it here again twice. You see, so imagine that we were to evaluate for fib of a larger number. There will be a lot of repeated calculations over and over. Yeah, those repeated calculations are the things that we want to avoid, and actually those repeated calculations are what gives us this concept of overlapping subproblems. So when we say overlapping subproblems, so it's the fact that there are subproblems in the process of solving for a particular number that are distributed over different points in the decision tree. Yeah, so this is a subproblem. Fib of 3 is a subproblem. Fib of 2 is another subproblem. But the problem now is that we need to evaluate for fib of 2 several times at different points. We don't have to do that. And first of all, that is what is meant by overlapping subproblems. And the way dynamic programming helps us is to remember the fact that we have computed these subproblems before. So we need to remember previous computations. These concepts is called memorization. So when it comes to dynamic programming, the easiest way to think about is we need to create a relationship between the subproblems. Yeah, so if we can create a relationship between subproblems like this one, where we can sum them up, and then we need to have a recursive function that eventually lands at a base case. Very important point. And then once we get the base case, from there on we can continue to split up, and then we need to memorize every solution that we've gotten so that we do not repeat solutions. So let's see what the pseudocode will look like in solving for this problem. So imagine that we have, so let's hypothetically speaking, say that we have like a function that is called Fibonacci, and this function takes in an integer parameter. So here's what is going to happen inside this function. First thing is we need to or rather, let me not say the first thing. What we need to do is we need to just say return, figure of n minus 1, return figure of n minus 1 plus figure of n minus 2. This is actually what we need to do. The problem is we can this is you can already see the problem. We are just going to keep creating a repeated function call over and over. It's going to be a lot of function calls, on the stack. So what we need to do is we need to figure out a way to stop, and that's where the base cases come again. So these base cases that we've spoken about before, fib of 1 and fib of 0, we need to have them here such that we say that if n is equal to something like, if n is equal to 1, you return 1, and then if n is equal to 0, we return 0. So, but we can be smart about this and then tell ourselves that we don't actually need to write out these two conditions. We can write them out as one, and then say that if n is equal to 1, or n is equal to 0, we return n. Remember, if n is 1, return 1. If n is 0, return 2. So we have these two together, just return n. So basically, this is the solution to the problem. But this solution now is basically going to explore the entire tree and give us this picture. We'll be evaluating for fib of 2 several times, fib of 3 several times. So if our initial n is 5, but if we need to evaluate for a larger number, you can imagine that we'll be repeating fib of 2 several times, 3 several times, 4 several times, potentially 5, 6, 7 several times. All of those computations are the things that we want to avoid. That's where memorization comes again. So what we just need to do here is simple. You just imagine that we would have a data structure. It can be a map. So the map will be a map of key to a value. So the key can be the input to this function, so an integer, and then the value is going to be the output from that function. So usually some languages have a definition for the return type. So here now you're returning back an int. So it could be int to an int. And remember, this is the parameter that is passed in, and this is like the output. So we map this to this. So what now happens is, at this point, after we return from here, we can easily just check. We need to check if it happens that the map already contains this value. We need to check if the map already contains the value n. If it does, then we'll return the value at that n. The reason is because if the map contains this key, that means that there's a value there. So what that also now means is that before we return back any one of these answers, we should, okay, do I select just, I want to select just this guy. Okay, something we can do. Okay, so that means just before this point here, we need to memorize, we need to store this value. So instead of returning this now, what we will now do is we need to evaluate this, say that we store this inside a variable. We can say int, like this will be our value. Value will be this plus this, and then once we have this as our value, the next thing is, okay, I think I need to shift this a little bit further down. So once we have this as a value, the next thing is we now need to store this value inside the map. So we need to now put the value inside our map. The key will be the n. Yeah, remember key. Why the value will be what we are going to return back, which is now this value. And then once we do that, we just return back the value. You see, so this is a little bit messy, yeah, but I mean, I just wanted to have like a small pseudocode just to show what the memorization looks like. So what happens with this memorization is, you can imagine that when we get to a point when we evaluate for 2, we store the value for 2, say we calculated it before. Then at some point, at some later point, if we need to evaluate for 2 again, we don't calculate all of this. We just check. The map just says that does this value already exist within the map, and it says that 2 already exists, and immediately returns it back. We don't need to evaluate for this. Yeah, so that's what memorization does for us, and it's an important part of dynamic programming. So for that now, we can just quickly evaluate the complexity of this, and it's, I mean, it might not be easy to see, but basically the complexity of this recursive approach that doesn't include any form of memorization is 2 raised to power n. And the reason, the time complexity, actually, so let me emphasize that time complexity is this. The reason for that is because at every point, for every evaluation of n, we split the recursive function into 2. So we make 2 recursive function calls. And we keep making 2 recursive function calls until we get to the base case. So that's why we have this 2 raised to power n. As mean we were to, it happened that we needed to split this into 3, then it will now be 3 raised to power n. Yeah. But now with memorization, this memorization step, what now happens is we do not continuously divide every problem into 2. Yeah. Remarkably, we only evaluate for all the n's once. So if we have n raised to power 500, we only evaluate for n raised to power 49 once, n raised to power 100 once, n raised to power 99 once, n raised to power 50, when n is equal to 50 once. Every number there in that part to evaluate for 500, we only evaluate them once. And that means that the time complexity now becomes O of n. You can imagine. So imagine an exponential time complexity becoming a linear time complexity. That is the power of dynamic programming and memorization here. And the other thing that is probably reasonable to remember is the fact that sometimes people say that dynamic programming helps to reduce an exponential time solution to polynomial. So what that means is that a solution that gives you a complexity whereby the input size, right, is the power in the time complexity analysis. The input size no longer becomes a power, it's no longer exponential, right? It now becomes a polynomial. So polynomial in the sense that whether like n squared, and this is now n raised to power 1, by the way. So n raised to power 1, n raised to power 2, n raised to power 3, or some form of multiplication or some other analysis with n, but then it's no longer like exponential. So yeah, so that's why this is good. In terms of space complexity, actually this solution doesn't really have any impact on the space complexity. The reason is because we only have a recursive call stack, and then the call stack is only going to be like the height of the call stack is going to be maximum the length of n. So what that means is that regarding space complexity, it's going to be of n, which is the size of the call stack. Yeah, so this is a solution for this problem, and then this actually explains what we meant by this question having an optimal substructure. You can see that helped us here in analyzing this. We need to split it down into 2. That's this part. Yeah. The other part is of the overlapping subproblems. So the fact that it has overlapping subproblems means that we could do this, save the answer to previous computation, and then reuse the answer. So that's how it helps us. One other thing that I probably should mention is the fact that For dynamic programming, there are several ways to solve them. Yeah, so some people say they are pull approaches, some people say they are push approaches, some will say there is a top-down approach, and then there is also a bottom-up approach. Yeah, so this is actually will take some time to really understand what they mean, but they can be a little bit confusing at the beginning. Well, it suffices to say that this one that you're seeing here is a top-down approach. Yeah, so we starting from the top, from whatever number we're given, like 5, and we are going all the way down to the base cases, and then from there we're going to come back. So that's a top-down approach. The other thing is that there's also a pull based DP, in the sense that we go down to go and pick the answers to previous ones and pull the answers together to form the answers to the original problem. Yeah, so that's really what I can say for now, but with time I think it's going to make sense. But that now brings the question of what is the bottom-up approach. Yeah, so the bottom-up approach is another programming. Let me use a different color here so that. And so when it comes to bottom-up approach, usually this involves some kind of iteration. Yeah, so instead of using this, we can use iteration. And yes, I'll just show you so that it makes sense. So imagine that we can have, I mean, when we need to evaluate for fib of 5 now, for example, we imagine that we have an array, and this array is like all the indices there. There are, let's say, let's say 6 indices. 6 now, yeah, 6, so that we have an index for 6. So we don't need this one. This is 6. So what we now do is that we say that this is a fib array. We know what fib of 0 is. Fib of 0 is 1. Fib of 1 is 1. And then we just have a for loop for for int I is equal to 2, and then I is less than or equal to n, and then we loop all the way. We just say that okay, fib of I is simply equal to fib of I minus 1 plus fib of I minus 2. So you can imagine that once we do this and we loop through, because we are going all the way from 2 to 3 to 4, that means by the time we are evaluating for 4, we already have the solutions for 3 and 2. By the time we are evaluating for 5, we already have the solutions for 4 and 3. By the time we are evaluating for 6, we already have solutions for 5 and 4. Yeah, so in this case now, when I is equal to 2, yeah, we'll say that okay, f of I is equal to f of I minus 1 plus f of I minus 2. So here will be 2. So then I now becomes 3. Yeah, and then we now say f of 3 is equal to f of the one before and the one before, which is 3. Then when we get here, I is now 4. F of 4 is now because this one and this one. Yeah, so you can see that by the time we are evaluating for every subsequent number, we've already seen the fib of the previous 2 numbers. Yeah, and then you can see that this time around, you can imagine this is also like a memo. It says that we remember the solutions to the previous problems that we solved. And this is actually like the memorization pattern when it comes to this approach. And then the other thing is that we are solving this problem starting from the base cases 0 and 1, and then working our way all the way to the solution that we've been requested to give. So at the end of the day, we'll now return, so imagine that this is at the same function call. We'll just return fib of the parameter that was passed in, which is the n. So you get, and then that will be fib of 6, which will be this 13, whatever the n is. Yeah, so we are starting from the bottom and then we are going up. That is where the bottom up comes up. That is what is meant by the bottom up approach. Yeah. So, and then this is also a pull based DP. Yeah, because when we are here, we want to solve for the 2 previous ones, so we pull the answers from the back. Yeah. So for push based DP, I can depict that with these 2. Yeah, but it might just be a little bit tricky, but I mean it can be done. I'll just I don't think I should do that now, or you know what, let me just do that, yeah, so that we get the full picture. So let's say that, so the push based approach, So the idea here is, remember the ones that we say we are pulling. Yeah, so we are here, we pull from the two previous indices. So here now what we do is different. It's the same idea. We are going to memorize all of this. Yeah, but then we push. So remember that when we say fib of n, what is this? Is equal to fib of n minus 1 plus fib of n minus 2. So in this case now, what now happens is, imagine that we are, we are at some arbitrary point. So let's say this is 1, 2, so we know fib of 0, we know fib of 1. Yeah, so we don't know these ones. These are the ones that we want to calculate for. Yeah, so now at this point, to figure out the solution to this problem, we say that, remember that for fib of n, we needed to pull from here and here. Yeah, but this time around, what we'll be doing is we're pushing the answers forward. Yeah, so what that means is that from 0, we push the answer for fib of 0. We push it forward. So initially, in this case, we'll need to set this as 0, starting at 0. Yeah, so we push the answer for this here, and then we push the answer for 0 here. So that's so that here we have 1 and 1. Yeah, then we go to 1. We push the answer for 1 forward here. We sum this to the next index so that this now becomes 2. Then we also push this here, so this is 1. So by the time we get to 2, we push the value for 2. We push it once, 1 index forward, and push it also 2 index forward too. So here this becomes 3, and then this becomes 2. Yeah. What is this? This is acting a little bit weird. This is 2. Then from here 3, we push the value for index 3 1 step forward and then 2 step forward. So remember that we have 2 here. So now this now becomes 5, and then this becomes 3. Yeah. So here we push the value for index 4 forward once. So 5 plus 3, this becomes 8, and then we push this guy. Then we also push it twice. This is 5. Then for this index, we push the value here forward once and then forward twice. Yeah. So once it becomes 8 plus 5, 13. We can no longer push it any step forward anymore. Yeah, because that's the end of the index. We are at the end of the day, this is our answer. So you can imagine that the solution will be something like look from fib of, create an array. Fib of 0 will be 0. What is this? Fib of 0 is equal to 0, and then we now say that we're going to now look from 0 all the way to 6, from 0 all the way to n, and then we push the value in that index of 0, into the next index and into the next one. And that is a push based DP. Yeah, and yeah, so that explains the last concept of push based DP. There's one more thing that is important for me to mention, which is the fact that this approach, this bottom-up approach, allows us to save on space. Remember that when we spoke about the top-down approach, we said the space complexity is of n. Yeah. So when it comes to the bottom-up approach, we can remarkably improve on the space complexity actually, and then the space complexity now becomes constant space. The reason is because remember that at every point when we're evaluating for a particular index, we only need the value in the previous index and two index before that index. We don't need every other thing. So for example, when we are evaluating for fib of 6, we only need fib of 5 and fib of 4. We don't need fib of 3, 2, 1 any longer. We only need 4 and 5. When we are evaluating for fib of 4, we only need 3 and 2. We don't need all the previous ones. Yeah, so we cannot skip like 2 variables to say, okay, this is 2 steps before, and then this is 1 step before. And then once we evaluate for 1, we replace those values and we only keep values from 1 index before and then 2 indexes before. That way we save on space. That's constant space. So that's what the bottom up kind of like helps us to do. Like usually it helps us to be able to find opportunities to save on space. Yeah, it doesn't really do so much when it comes to improving the type complexity analysis. Actually, it just really helps for space. Yeah, so that is more discussion about the Fibonacci numbers pattern. All right, so thank you guys for joining me once again. See you guys in another video where we'll be talking about the next dynamic programming pattern on this list, which is the 01 knapsack problem. Please don't forget to like, share, and subscribe. See you guys in another video. Bye.